So welcome to all my student friends. Today we are going to discuss the various problems and solutions in the first unit, whatever we discussed in the previous sessions. Okay. Mainly these problems concentrate on mathematical model, dynamic analysis, block diagram reduction technique, signal flow graph, and feedback principles. Okay, so these are all covered under uh, unit 1. Okay, so what is a transfer function? Mathematical model is nothing but a gain of a system. That is, mathematical model consists of a set of mathematical equation. So it is also called a transfer function model. It is also called a gain of the system, open loop gain of the system, so etc. So how to determine the transfer function? What are the various methods to determine the transfer function? So what are the various methods? First method, the various methods, okay, various methods used to find transfer function model. So what is a transfer function model? Basically, Laplace transform of output to Laplace transform of input. Okay, that is the transfer function definition. So how to determine the mathematical model? Use transfer function model using mathematical model of a system. Mathematical. If you obtain the mathematical model of the system, then we can easily determine. Okay. Then next method is block diagram reduction technique. Okay, block diagram reduction technique. The third method is signal flow graph method. Okay. Fourth method is pole zero plot. From the we can also determine the transfer function model from the pole zero plot. Pole zero. What is pole? What is zero? Okay, poles are nothing but the denominator factors of the transfer function model. Okay, transfer function model. Say g of s equal to some s into s plus 3, s minus 1, s plus 2, etc. So the denominator part, the roots of the denominator is called poles. The roots of the numerator called zeros. So 1 0 at s equal to 0, 1 0 at s equal to minus 3. In the poles, one pole at s equal to 1, one pole at s equal to minus 2. Okay, s equal to minus 2. So from using this pole zero, say pole zero plot in S domain, we can draw the plots. Okay, from S domain, the x-axis is real and the y-axis is imaginary. So we can plot poles and zeros in the domain. Actually, we can't say poles always real. So poles may be real and equal. Poles are imaginary, complex. Poles is real and distinct. So likewise, there are different poles. So using the pole characteristic also, we can be able to determine the transfer function model. The next technique is root locus technique. Root locus technique. Then we can also determine from the Bode plot, frequency response plot, Bode. From the Bode response also we can able to determine the transfer function, Bode plot. It is comes under frequency response. We will discuss later. Okay. Then we can also determine from the state space model. State space model. So these are all some important techniques used to determine the transfer function model. Clear? Today, let us model this dynamic system. It's a mechanical system. How to model this mechanical system? and how to obtain the equivalent electrical system for this mechanical system. First, let us find the transfer function model for this rotational system. It's not translational, it is a rotational mechanical system. So first identify how many number of uh, uh, mass related components here. So how many number of mass? Say J1, J2 are mass related components. In translational system, it is M1, M2. In a rotational system, it is J1, J2. Similarly, in a linear system, X, linear displacement is X, X1, X2, etc. Here, theta 1, theta 2, theta 3. In a linear system, velocity, here d theta by dt, omega, angular velocity. Say how to get the mathematical model from this system. So how to find transfer function of the system. Okay, transfer function. First, divide this this entire diagram into two nodes, like a nodal analysis. So first I consider the J1. First I consider J1. So we can write the force balance relation using Newton's law, right? Newton's law. So what are all the forces interacted with the J1? So what are all the forces interacted with the J1? First, T, torque, okay, torque. So torque is a one force, torque force acting on the J. Next, say this is torque. Next, force due to B1, then force due to K1, then force due to the self mass. Self mass is moment of inertia. What is the force Fj? Okay, so what is the output for this? So theta 1 is the output for this J. So the displacement is theta 1, the velocity omega 1. Okay, so first you draw the free body diagram like this. So first draw the J, then J1, J2, J3, etc. Then you first mark the various forces acting on the J1. Okay, then write the relations. Write the relations for this. So what are the relations? Force due to B1. What is the force due to B1? So B1 d theta, it is purely in the theta 1. Okay, so theta 1 d theta 1 by dt. Then what is Fk1? You have to carefully look into this matter. Say the K1 is the spring constant. The spring links between J1 and J2. This theta 1 develops J1, theta 2 develops J2. So when you go from when you do the analysis from this side, you put theta 1 is more, theta 2 is less. So K1, we should write the difference in displacement, theta 1 minus theta 2. Understand? So next, Fj1, the self mass, Fj1. So moment of inertia of d square theta 1 square divided by dt square. Sorry, d square theta 1 divided by dt square. So this is J. So these, according to the force balance relation, torque equal to Fj1 plus Fb1 plus Fk1. Understand? So this theta T equal to J1 d square theta 1 divided by dt square plus B1 d theta 1 by dt plus K1 theta 1 minus theta 2. Let us have equation number 1. Next, for the next node, you draw the free body diagram. What is the next node? J2. Okay. Now, FK2. Say FK1 is also acting here. FK1, FB2, K2 also there, right? FK2. Say on this friction is there, this spring both are acting on the J2, then there is no external force here, so no torque, so developed torque, so that is 0. Okay, so what is the force acting on the J2? So then force due to J2, so J2 d square theta 2 divided by dt square. Then plus B2 d square, sorry, d theta by theta 2 by dt plus what is due to Fk1, K1 of theta 2 minus theta 1 plus K2 theta 2 equal to 0. This is equation number 2. So this is the two relations related to the two nodes. See here, anything else? Okay, good. So these two nodes, we can also write this relation as in terms of omega. Okay, we can also write in terms of omega. So you know that omega equal to d theta by dt. Then what is theta? Theta equal to integral of omega. If you bring to this side, integral of omega dt. So here what I am going to do here is, I am going to modify this relation, the equation number 1. 1 by, see here, T, J, J1 d omega by dt plus B1 omega 1 plus K1 integral of omega 1 minus omega 2 equal to d. Keep it as equation number 4. Similarly, you write the expression for this system. Okay, so equation number 2. J2 d omega 2, sorry, here is d omega 1, d omega 2 divided by dt plus B2 omega 2 plus similar to this K1 or K2, first write K2 integral of omega 2 plus K1 integral of theta 2 minus omega 2 minus omega 1, omega 2 minus omega 1. So what is the analogous to electrical system for this. So first we do torque voltage analogy. Torque voltage analogous system. So please refer the previous notes. So what is the relation between torque voltage and torque current? Okay, what is the torque voltage analysis? Here torque equal to voltage E of t. Okay, then moment of inertia equal to current. Moment of inertia equal to current. J1 equal to I1. J2 equal to I2. Sorry, LD square by dt, right? In this, right? Because this is the second order. Sorry, this will be L1. Moment of inertia. L d square 5 by dt square, that is I. Okay, omega is omega only I. Here omega only, I think we will get I. So J1, J2, L2 inductance. So please refer the previous class notes. So moment of inertia, J1, J2, L1, L2. Omega 1, omega 2, omega 1 equal to I1, omega 2 equal to I2, B1, B2, the friction equal to R1, B2 equal to R2, K1, K2, K1 equal to 1 by C1, K2 equal to 1 by C2. This is the analogous relation between the torque voltage and torque current. Just you replace this thing in this equation. So what is this equation? J1. What is instead of J1? What is there? J1 L1 d I1 by dt, because here you see instead of J1 we put L1 5 I omega 1 I1. So L1 di by dt plus instead of B it is R. Okay, R into I into R plus K1 instead of K1 1 by C. What is omega I1 minus I2, right? Very simple. L1 di by dt plus B instead of B it is R. Just realizing the RLC network, series and parallel network. R into R1 I, R1 into I1 plus 1 by C integral I1 minus I2 equal to torque. This is the equation number. Say here in this case you consider 1, or what is the last 4? Says this is 4. You can take this as 5. Consider this equation as 6. So similarly, for the second equation you can write L2 di2 by dt plus R2 I2 plus 1 by C, sorry, here it is C1, here it is C2, integral of I2 dt plus 1 by C1, 1 by, yes, 1 by C1, integral of I2 minus I1 into dt. Say equation number 7. Okay. If we simplify these two, okay, if we simplify these two relation, you will get the diagram. Okay. So what is in uh, the torque applied is in series with the inductance. Okay. In a closed loop circuit, there are two equations. So definitely there will be two loops. Okay, two loops. So if we have two loops, in the first loop, the voltage rise equal to voltage drop. Okay, what is voltage rise here? Sorry, here also I made mistake. This instead of torque, E of t. Okay, instead of torque, E of t. See here, torque is E of t, J1 is inductance, moment of inertia is inductance, omega 1 angular velocity is current. Okay, so you can ask me, sir, what is theta? Theta is the displacement, the flux is the equivalent flux, right? So d phi by dt equal to I. So I equal to d omega by dt, right? So I equal to d phi by dt. So phi is the displacement here in the flux, equivalent to the flux. Okay, so when you say you consider this equation exists on the first loop circuit. So in the first loop, what are the things? One inductance is there, in series with the resistance is there. Okay, then a capacitance. Capacitance is between I1 and I2 loop currents, two loop currents. So you have to place the capacitor middle. That's all, very simple. Then equal to E of t. Please, if you have any doubt, ask me. Vignesh. Vignesh.
Yes, sir.
Do you understand what I am saying?
Yes, sir. Yes, sir.
Okay. See, according to the equation number 6, the voltage rise, say E of t, it is voltage rise, E of t equal to L1 R1. So in the first loop, I1. Okay, very simple. Here, see, the 1 by C, the capacitance is between two currents. So it is at the middle. So we can place the C value here, 1 by C here. So 1 by C1. That is C1, right? So actually it is in the relation C1. In the second loop, what are the components in the second loop? L2, one inductance in series with the resistance and capacitance in series, and the capacitance between the two currents. So the purely one capacitor is in series with the I2. So here one more inductance, one resistance, one capacitance. So this is C2, this is R2, this is L2, again current I2. See, as per this second loop equation, L2 d I2 by dt, d2 by dt plus I2 R2 plus 1 by C2 I2 plus 1 by C1 of I2 minus I1. This is the force required torque voltage analogous system. Clear? So this is a torque voltage analogous system. Next is torque current analogous system. What is the torque current analogous system equivalent? See, in that torque current analogous. Torque equal to current, I of t. Torque equal to current. Here, the friction dashpot equal to 1 by R1, B2 equal to 1 by R2. Okay. J1 equal to C1, J2 equal to C2, K1 equal to 1 by L1, K1 equal to 1 by L1, K2 equal to 1 by L2. Now, just to replace these two equations, very simple. You can we will be easily getting. So, what is J1 is C1. So, what is the equation here? J1 is C1, B1 is 1 by K1, K1 is 1 by L1. Okay, 1 by L1. So, C1, similarly, here omega equal to T equal to torque equal to current, So, K, C, J, so we are having J equal to C1. So J relation is J d omega by dt. So when omega, what is omega here in current analogy? If this is C dV by dt, right? So current I equal to C dV by dt. So good. So here C1 dV1 by dt plus 1 by R1 into V1, right? Into V1. V by R equal to I, right? Good. Plus 1 by L1. So what is current? 1 by L1 is constant. That is voltage. Integral of voltage V1 minus V2 dt equal to I of t. Similarly, C2 dV2 by dt plus 1 by R2 V2 plus 1 by L2 integral V2 dt plus 1 by L1 integral V1 minus V2 minus V1 dt. Am I right? So please carefully see these relations. What is that? So current, when you go for torque current analogous system for electrical system, here only uh, almost all the voltages are constant. All the voltages are constant means it's a parallel system. Only variation is at the inductor. Only variation is at the inductor. So this is common to parallel circuits. If torque current means the circuit is parallel RLC network. Circuit is parallel RLC network, right? So what is the analogous system for this equation? Clear? So what is the analogous system here? So current I of t. So there are, see, in have it as so this is, I say we can consider this is IC1. This is IR1. This is actually this inductor is common to two parallel networks. So two parallel networks. Okay. So this is IL1 between two parallel currents, right? So similarly here you can write as IC2. This is IR2. So this is IL2. So this is similar to common to both networks, two parallel networks joined together by a inductor. So let us draw. So I of t is the excitation current force. Here is force is I of t. So the I of t is dropped across one capacitor. Okay. So what is that capacitor? C1 dV1 by dt. So that is C1. Clear? So C1, this is R1. R1 also across B1. So there are two parallel loops because of two voltages are there. So R1. Okay. So another network is, if you write the equation for this one, C2 V2. So another voltage drop across capacitor, another voltage V2 across resistor. Okay. So here you can write another capacitor C2 whose voltage across this capacitor is V2. Similarly, one resistor R2. So across this C2 V2, across the voltage across R2 V2. So these two are common here. Okay. So what is one more thing is there? One more thing is what is one L2 is there, right? In the L2, you see the L2 is that is also IL2. This is across the V2. So one inductor here also, one inductor. So L2. So what about L1? L1 between two voltage networks. So draw L1 here. So this is L1. So current I is passing through to here. So some voltage drop is here. So because of the current passing through the inductor, this inductor drops some potential. So remaining potential only pass to this side. So potential across this network is V2. Potential across here, this side is V1. So across here is V1. Across the potential drop across here is V2. So this is for torque current analogous system. So very important. Objective type questions will be asked by giving this type of networks. So what we seeing from a mechanical system, obtain the dynamic equations of the mechanical system shown in figure. Also obtain the torque voltage and torque current analogous system. Clear? So this is first we modeled the mechanical system. We derived the dynamic equations. So 1 and 2. So from the equations, we converted from mechanical system to electrical system. Then we drawn the electrical equivalent analogous circuit. So this is for torque current analogous circuit. Understand or not? Next question is, so in a second order instrument, K is the spring constant, M is the mass of the instrument, and B is the damping coefficient of the instrument. What is the damping ratio? What is the damping constant necessary to just prevent the overshoot in the step responses? How to prevent the overshoot? Actually, the overshoot depend on zeta, the damping ratio, zeta. Okay, damping ratio, or it's also called damping constant, coefficient of friction constant. Like that, we can also tell. The terminology vary from one place to another place. We can classify the system according to zeta value. So the zeta value normally varies from 0 to 1, between 0 to 1. If zeta less than 1, called under damp. Under damp. If zeta greater than 1, over damp. Over damp. If zeta equal to 1, critically damp. Critically damp. If zeta 0, undamped. Okay, so the zeta varies from 0 to 1. So zeta is 0, undamped. Undamped system. Here the question is, it's a second order instrument. So normally the second order instrument consists of generally with a mechanical system or an oscillator. The transfer function is say y of s by x of s, or transfer function t of s normally equal to 1 by s square m plus sb plus k. So this is the second order instrument transfer function normally. So what we have to do, say the 4 options also given in the examination gate. First option is whether to avoid overshoot, we should prefer critically damped system. We should prefer critically damped, means zeta equal to 1. We should find out the condition for zeta equal to 1. So this is a second order instrument. So I already informed you that the closed loop transfer function of the second order system is omega n square divided by s square plus 2 zeta omega ns plus omega n square. Okay, so just we bring this denominator to this form. Okay, what is here? S square coefficient is 1. So how to remove this? Remove m outside. Okay, 1 divided by m s square plus b by m s plus k by m. Last class also I explained we should compare this form and this form. The standard form, the standard second order transfer function, closed loop second order transfer function with this form. Okay. So first always compare the constant term, the last omega n square term, the constant term. First always compare the constant term. So compare the constant term. What is the constant term? Omega n square. Okay. Omega n square. The constant term is omega n square equal to k by m. So what is omega n? Square root of k by m. Okay. Square root of k by m. So next we should compare the s coefficient. So whatever the s coefficient available in this equation. So what is s coefficient here? 2 zeta omega n. So on comparing s coefficient, what do we get? 2 zeta omega n equal to b by m. So what is zeta? Zeta equal to b by m to omega n. So what is b by b to m? Okay, m. What is omega n? Square root of k by m. You bring this m to inside the equation, so we will get we'll be getting 2 square root of km. Okay, this is the value for zeta. Zeta equal to b by 2 root of km. So to settle the system without overshoot, the zeta value should be equal to 1. So when this equal to 1, what is b? So b equal to, this b value equal to 2 root km. So which answer is correct? So which answer is correct? The overshoot, the step response of the system is equal to 2 root of km. Okay, then zeta value equal to 1, 2 root of km. So this is the correct answer. So for the correct answer is 2 root km. Any doubt?